Hey, it says I'm Lars.
His computer.
Yeah. Wait, I'm going to make a title for myself. Give me a second.
No, I'm already.
Really? Are you doing it? Floor is sitting over there doing it.
Ah, I know.
Nice.
So we have an actual audience sitting over there, which makes doing Amsterdam Ruby meetups, well, scary as they used to be. That's fun. I already told the audience because, well, we had so much time on our hand because we delayed it by 15 minutes. No, it was because we had so many technical difficulties that I had to write whatever I was going to talk about here. Anyway, how do you open a Amsterdam Ruby meetup after months of not having in real life Amsterdam Ruby meetups? Well, with a welcome. Hello, so happy to have you all here. It's going to be fun. Welcome at the 17th of May Amsterdam Ruby meetup, where I think we have to rename this thing. I'm looking over there all the time to Floor, who's actually doing the well, hard work here. That we're just going to rename to the episode where all went wrong, because we have a camera that's not working. We have microphones that we can't connect. We even have a second camera still underway. It was so much easier from home. Anyway, let's talk about things that are actually important. So this Amsterdam Ruby meetup group has a code of conduct. And that means that me, for instance, the peeps in Slack and Twitter and, well, everyone here, everyone there is, going to abide to these rules. They are fun because they make this meetup more fun. They make the community more fun. So if you can't sleep this evening, read it. There will be 2 talks today. During the talks, you might have some questions just popping in your head. If you are in this actual room, but there are really people there. It's insane. So you can ask your questions in real life. If you're not here, you can post your questions in the YouTube chat. That means that Floor will probably relay them to me or put them in the screen, and I'll ask this speaker or the second speaker those questions if they can't read it for themselves, because, well, who knows. So the YouTube chat for questions. Then, of course, I already mentioned we have Slack, where we're going to have more discussions. Potentially, you can ask questions to the speakers there tomorrow. I don't know if the second speaker is there. We need to invite them. Anyway, join the Amsterdam channel for, well, the Amsterdam meetup thingy, but general is usually way more fun. Then definitely you can talk about us. We have Twitter. I haven't seen Twitter for at least a week, which is so zen. Anyway, but Amsterdam Ruby does have Twitter, so follow us, talk to us, talk with us, annoy us. That's what Twitter is for. Anyway, we're streaming this thing to YouTube, and, well, you can see for yourself tomorrow, because we're also at the same URL that you're going to bookmark. Yes, start bookmarking it. Anyway, you can just have a look at the video tomorrow or whenever this thing is over. If you're listening to this thing when the thing is over, that sentence did not make a lot of sense. Anyway, so we have YouTube. There you will see the videos. I already mentioned we have 2 speakers. That means first, Lars from Zilverline, who is, by the way, sponsoring, which makes me really happy, because pizzas, because just people in real life. Then he will be introducing the company Zilverline, I hope. But he will also have a fantastic talk about Ruby fibers. Then we're going to have a 5-minute break so I can just dive into more technical difficulties. And then we have Jonathan Boccara, who I didn't meet before, so I'm just guessing that this is how I pronounce his name. He's the principal engineer at Doctolib, with a talk about tests. Anyway, but that's for later this evening. Now we're just going to have a look at the presentation from Lars from Zilverline.
Thank you. Okay, I guess I need to, let's see. Yes. Is this okay for the recording? Okay, welcome everyone. So welcome at Zilverline. My name is Lars Vonk. I'm one of the owners of Zilverline, so I can have a small commercial talk. You might know us from the bookkeeping program Yort or from our home automation solution Tinka. If not, it doesn't matter. And more reason to join us. We're looking for new developers to join our teams to work on great products. So if you're interested in the break or after the presentation, talk to me or any of my colleagues present here. Yeah? So
Lars, are you on Slack?
I am on the Ruby Slack as well. Yes, I'm not on Twitter. So much in.
So, but if they join the Amsterdam Ruby Slack thing that we just showed, they can also talk to you?
Yeah, they can also talk to me just by my real name, Lars. So shoot me a message.
That's going to be easy. Thank you.
Yes. So this talk originated from one of our internal knowledge sessions that we have. At Jot, we are moving away from a delayed job as a background processing because it was not scalable enough, and we're slowly migrating to a more scalable solution, and therefore we're also looking into Ruby threads and Ruby fibers. And the actual moment it got my attention was when I started to upgrade to Ruby 3. Then I read the changelog, very advisable if you do an upgrade, major upgrade, read the changelog, what you should change. And there was this announcement that the Ruby scheduler was released. And I didn't know that fibers already existed in Ruby 1.9. But they added a Ruby fiber scheduler in 3.0. So that makes me then wonder, so what is a fiber scheduler anyway? I don't know. And maybe I'm alone in this, but I guess not. Then I start clicking links and start reading and clicking more links. And before you know it, your browser looks like this. And then it's time to go to the source of truth, like real books. So this Ruby Fiber post made me buy this book by our professor Tannenbaum to see what are actually processes and threads. Because I've been programming since 1999. I was hired as a school dropout to fix the Millennium Bug. So you all live, so that works. No thanks, by the way. You can thank me later. And I've first been programming in Java, and that already is working a lot thread-based. So I was already familiar with working with threads, but I'm a programmer, not a system engineer. So I know how to use them, but what's the actual definition of it? I never really realized. So this made me dive into this a bit more. And before I'm gonna show that, I have a few small quizzes. So who here already works in Ruby with threads and is familiar of the concept of threads? Yeah? Fibers maybe even, or threads in other languages? Yeah, okay. Then I expect some answers from you guys. So this is also still, yes? Okay. And copy paster. So we have a small program here. And it is called, is this small program? Responding. So, how many threads do you think is started by this program?
Sorry.
Yeah.
You're sharing your presentation.
So I should share my
Yeah,
whole
you can
screen.
share the screen now.
Yeah. Okay.
He did it on my request. It's not him, it's me.
Sorry. Are we back? Yes. So, how many threads does this program start? Anyone? Two. Three. Anyone else? Another? That's a good question. It depends. So let's first run it. So I print here the number of threads, right? Thread list.count. Oh, I'm in the herb. Sorry. Yes. This is very good, but it's the wrong answer. This is from a Ruby perspective. Now let's look at the OS. So this is the pit, and you can do ps minus m 4. From the kernel's perspective, there are 4 threads. So any clue what that other magic thread is? Because it's 3 and not 2. Because the main thread is also a thread. Then you start 2 and have 3. But there's another thread. What's that thread doing? Yeah, monitoring.
Ruby virtual machine.
Yeah, what does it do?
Compiling everything.
It's a scheduler.
Yeah.
It's a thread scheduler that makes sure that each thread gets an equal amount of time to run. So there are already different perspectives. You as Ruby developer, how many threads do you see and how many threads there are actually in the OS and the kernel? So let's do a quiz once. Thread scheduling. Yes. Okay. So like the other examples there's a thread scheduler, and this example shows how the thread scheduler works a bit. So we have one thread accessing something I run on localhost that waits 5 seconds, and another thread that just prints something and sleeps 1 second. Any predictions to be made on how often this thread is running versus this thread? That's 5 seconds.
Wrong answer only?
No, yeah.
I would say 5 to 1.
5 to 1, yeah.
In 5 seconds, not milliseconds, right?
Yep.
Okay, good.
Oops. So it was Ruby. I should first kill this. 4 minutes running, so I can do Ruby lib. What's it called? Thread scheduling. Five. Yes, 5. So works as expected. So that means that the first thread waits 5 seconds, it blocks, and then it allows the other thread to run. Yeah? We will discuss this more in detail later, but it was not a trick question. Okay. On to the next. So processes, threads, and fibers, what are these anyway? So I start processes all the time, I start threads all the time, but what is the actual definition of it? So then it comes from this book, Professor Tannenbaum, one of the inspirators of Linux and writer of Minix, I guess it's called, right? And a process is indeed described as a group of resources that are related together. Like an address space where the text and the program runs, global variables, open files, child processes, and a thread, or thread of execution, short thread. So each process has at least one thread. And then we have a thread next to that, which contains the program counter, registers, the stack, and the state. Yeah? So everything in a process shares the global variables, open files, etc. And each thread has an own program counter, register, stack, etc. So why do we need them anyway? Processes and threads. Very simply said, if you have a CPU, only one CPU, it only supports one single thread, maintaining one thread counter. So you can only do one thing at a time, which is of course very wasteful. A CPU can execute a command in about 1 nanosecond. So to put that in perspective, So if it, for instance, needs to write data from memory and it's not a cache hit, it needs to wait. And compared to 1 nanosecond, that's a lot of time. So if you compare 1 nanosecond to a second, then if one CPU instructions take a second, then reading 1 megabyte will take 3 days, and doing a round trip to the US 5 years. So for a CPU perspective, that takes ages, right? So that's why you want parallelism and stuff to be executed concurrently. I don't know if these values are still up to date, but I remember this talk from Eric Meyer, so I believe him. So therefore, hyperthreading was also invented, which basically allows you to have multiple threads for one CPU, right? So on the CPU level, the parallelism is created. So from an OS perspective, a hyperthreading CPU is basically the same as 2 CPUs. Then, since we're not hardware developers but software developers, how does that relate to us and what we do? So you have the kernel, you have the system call interface, stuff like read or I think write, and well, there are all kinds of system calls that go into the kernel to access something from disk or anything. And above, on top of that, you have typical GNU libraries. Of course, so for instance, Ruby uses malloc to allocate memory that lives in user space. And you have user applications, stuff that I create, and I think most of us here create. So there are 2 different kinds of threads. So you have user space threads that live on the user space side. So they're really fast. They don't need to tap into the kernel, which is a costly operation. But it's not possible to do blocking I/O. So if you read something from disk, internet, or basically anything else other than memory, you will block and nothing else can run. And then you have kernel threads. And kernel threads are in that respect better because they allow for blocking I/O. If a kernel thread blocks, then the kernel will make sure that another thread gets time to run. Yeah, that you don't need to do anything for that. So that's great. Thank you, kernel developers. So yeah, what is blocking I/O? Yeah, system calls that you need to wait for until completed, like read, write, and it's really blocking, so nothing else can run. So to compare, most Ruby applications I know are process-oriented, like passenger starts processes for each request to handle. Delay job is, for instance, process-based. There's some advantages, right? You're sure you don't write in each other's memory. You don't have shared access, well, except for the database, of course, which is the global master of all global variables. You have true parallelisms, of course, if you have multiple CPUs, or not with hyperthreading or not. But it also has some disadvantages, like it's more expensive in memory and also expensive in CPU usage, in the sense that it doesn't leverage the CPU to its full potential. And then you have, of course, kernel threads. Concurrency handled by the OS, so via preemptive context switching, preemptive scheduling, it's also called. And of course, the advantages of that is that it utilizes the memory and CPU better, and it's cheaper to create in a process, so it's faster to start. But on the other hand, program concurrency is hard because you have to constantly work with mutexes if you want to access shared memory. It's a bit different programming model than process-based. And still, less than a process, you could possibly have useless waits, and show some examples of that later. So enter fibers. It's already there since 1.9. I have no clue when that came out. Does someone know? Like 5, 6, 7 years ago or something? Each year one, eh? So we're now at 3, I don't know, a long time ago. And basically it works like this. You can create 2 fibers. They live in user space, by the way. You can have 2 fibers, you start it, you give one a block, and the other one also a block. And by calling transfer, you transfer from one to the other. So, I have no mouse, of course. So in the first part, so when we go to the next line, when you execute this, first line that will be executed is the last line. Ping transfer pong. This actually is quite mind-boggling, and I still have to think about how that works, because transfer does two things. The first time is a special time. So you pass in the one that you want to transfer to. That's pong, and that will be passed in as the first argument in the block. And then, so the next thing that's executed, you actually pass in the string. So not again yourself, but and then it's transferred to pair. Yeah. So this this fiber yields, stops processing, and then the pong fiber enters, and it prints, of course, the ping. And then ping says transfer pong, and that argument, what you pass in there, is the result of the pair.transfer. So this is how you can communicate between fibers. Yeah, with fibers other than threads, you as a programmer are responsible to schedule them. So you say, okay, I now yield control to someone else, and you have to also specify who that is. That's how you can do multi-threading or concurrency with Ruby without threads. Another way of doing it is yield and resume. You cannot mix these two, so you either use transfer or you use yield and resume. And it is a bit similar. So you define your two fibers, and you say here, you say resume, and you pass in the message. So it will first go to ping, then we immediately yield and go to the main fiber. So here also you have a main fiber, always a main fiber. So each programming in Ruby you start as a main thread and a main fiber, even if you don't do anything with it. And then you can resume pong, and it will do this and yield again. And then you're back in the main fiber, and then you can resume the other one. And we're back here. Yeah, any questions so far? Just raise your hands. Otherwise, I'll continue. So let's go back to our comparison table, user threads. So fiber is a form of user threads where you are the one who are responsible for handling the concurrency. So which fiber, yeah.
Quick question, what you just showed. So yield always goes back to the main fiber?
Yeah, where you come from.
Oh, where you come from, okay.
Sorry, can you repeat?
The main fiber, yeah, main fiber. That's what we saw. Oh, sorry, repeat the question.
Yeah.
So the question was, where does yield go back to? Let me quickly resume yield. Yeah, because you're in the main fiber when you yield. So it goes back to the fiber that yielded. So here we start resume from the main fiber, then the ping resumes, so you're back in the main fiber, then the main fiber resumes pong, that yields, and you're back in the main fiber.
Okay.
So the fiber who started, yeah.
So are these fibers global, or are they like grouped together within a thread?
Yeah, in a thread.
Okay.
Good. The question was, are these fibers global, or are they bounded to a thread? And they're bounded to a thread. Yeah. Okay. See the animations for free again. So fibers are also referred to as user threads. It means like it's you have to handle the concurrency, so you are in control of what runs where, when. Downside, of course, is you can't have blocking IO because then it blocks. So if it blocks, you cannot do anything as a programmer anymore. But the advantage is you don't have context switching, what you do have with threads. So you don't have to do an expensive kernel call. So it's very fast. It's memory efficient. It shares the same memory as the thread. Yeah, if you have multiple CPUs, then a fiber will by definition stick to one. So you can't do parallelism with only fibers. For that you need threads. Yeah. So how do you do then if we can't do blocking I/O? What can we do then? Because we can't really read from the database, go to the internet, or read from a file. If you can't do blocking I/O, you can't really do anything in your program, right? So I should show fiber blocking. That's what I'm gonna do. So how can you do blocking? I will make it a bit bigger in a moment, increase the font. So here I have a very small program, which is a timer, which waits, and then if the timer is done, it prints something using fibers. And here, hooray for one-line Ruby methods. I think it was 3.1 or something. So that's a nice addition. You have this call in Ruby to check if you can read from a socket, read non-block. And the interface is a bit weird because it throws a standard error if it doesn't, you can't read it, but it returns immediately. Right, so this waits for me to type something in, and then it will print what I typed in, and then it transfers to the timer. Yeah, it's very simple. And then here the timer, oops, is a small thingy that loops until it's elapsed, basically. So if I run this, so it prints the time each second. And if I type something, enter, it also prints my enter. But I do read from file. If you use normal read here, it will block and doesn't do anything. So read non-block will throw an exception if it's not ready, and you can continue. So this is how you use fibers. So you check for some resource if it's available, and then you read it. And if it's not available, you pass you yield to another fiber. And it's very powerful, because this allows you as programmer to utilize the CPU the best, because the Ruby thread scheduler gives each thread, I think it was 10 milliseconds, yeah, 10 milliseconds, and just pass it over, even if it's blocking or not. It always does it passes each thread 10 milliseconds around. Is that English? I don't know. Again, so in our daily life, we see blocking calls frequently. Find by, REST client post, file rewrite, all blocking. But as you can imagine, to first check if something is available and then do it, it's a lot of work, right? So we don't want to do that as programmers. Thank God for kernel threads, because they allow us to do parallelism and concurrency instead of us checking all these kind of things, which make your code quite unreadable. But luckily, there are some gems available already, like polyphony, I think you pronounce it like that, and async. Anybody know these gems, by the way? I haven't worked with them, but you do. No? Yeah? Have you worked with them?
We use async and polyphony on production.
Someone uses async on production, so that's good. Love to hear more about that later. So, hooray for Ruby 3.0. So the thread fiber scheduler to the rescue. So how does this help us? Well, basically, it provides a set of hooks that you need to implement that you will receive. So if you do a blocking call, it will give you a hook in the thread scheduler that a fiber is blocked on something, and that you can then use that information to pass or yield to another fiber. This is still a work in progress. As of the time that I wrote this, these were the hooks available, but I think there are more added quite fast. So IO wait, kernel sleep, address resolve. If you look up an address, for instance, blocked and unblocked. Blocked is for if you wait for a mutex, for instance. IO wait is of course for reading and writing from sockets, and so forth. So And the other thing is that scheduler interface is really an interface. Ruby provides no implementation. So it's up to the community, deliberate choice, to implement this. And async, I think, is already one that provides a production-ready implementation, and there are more, but I don't know them from the top of my head. But I, of course, implement my own with the help of the test scheduler that's in the Ruby core, by the way, which says don't use in production. Select is already something that you can use for checking if a socket is available. It's not recommended because it's slow, and there are better implementations for various platforms like ePol for Linux or KQ for Mac OS X. And I think async, you can see in the async code that they use these system calls to check for availability. The code, so I'm not going to go through all the ones, but a few important ones are nice. These are just RDocs to see what they do. So it starts with fiber. So whenever you schedule fiber, this method is called, and the suggested implementation is that you immediately resume that fiber also. So it can do something useful. Second important one is, of course, IO await. And if in a fiber you do a blocking call, this will this callback will be called with the IO that is blocking, some events that what it's waiting for, and a timeout. I think that one is optional. And then, of course, block, which is another way of something that is stopped your fiber from executing. I think it here gives, that's like thread point join and indeed a mutex. And the other one, it's a bit weird to me, but you have the close interface, and the suggested implementation should implement your event loop in the close method. So the last thing that is called in your program is like, okay, fiber schedule.close, and then your actual program starts running. And it waits until all the fibers are done, basically. There is, I made a very small, short implementation based upon the test scheduler in Ruby, just to play around with it a bit, see how it works. And runs, and I'm just going to show you some of the methods. So this is basically the main method. You define which scheduler you have on this line. Then you set the scheduler. This is what you need to do, just as the setup. And then if you want to schedule 20 fibers, you schedule a fiber like this, fiber schedule, and you pass the block that it should execute. And this is a very simple one. It just waits again for, I don't know, well, it depends on how many seconds, what I pass in, and then finishes, right? And given what I just said, then when thread schedule is called, it calls fiber, which does exactly what was recommended. So it immediately resumes the first fiber. Then one of the fibers, of course, will block on IO await. And here you need to then capture the IO that the fiber was waiting for, and pass in the fiber that is waiting, so you can resume it later. Yeah, and in this implementation, you separate the reads from the writes, so you know which one, and then it yields. Yeah, so it's, I can do because I'm waiting, so someone else can run. That's basically what you say here. And when that, so here's the close method. The test implementation then delegates to a run method. So name it run then instead of close, but okay. And here you see that it constantly polls those IOs for available. You already have, this is based on IO selects, which you shouldn't use in production because it's slow. But IO select is also a non-blocking call, which returns readables and writable sockets, basically, that you can then use and do something with it again. So, for instance, here you can say, Where is it done? So each one that was readable and that can now be read is put in a selected hash with a fiber, and here we resume them again. That's basically how it works. Same for the writables. But here you see that you as a programmer need to say, okay, I was waiting for this, but now it's available again, so you can resume again. You don't need to write this yourself, of course. There are excellent gems already available. But it's good to understand what's going on by playing around with this. And the same goes for basically all the stuff you can wait. So we can wait for blocked stuff, which will now be unblocked, for instance, etc., etc. There was one funny thing, which I still don't understand why it's there. So hopefully someone in the audience knows. There is this urgent pipe created, which is not like written to when something waits. So my suspicion is that it has to do with how IO select works, because it is some sort of trigger to make sure that this selecting works. Anybody know why this urgent thingy was put in there? Yeah?
They might have added it so that certain bits of code could sort of manually wake up the schedule.
Okay, so you're saying that it's there to... Yeah, I'm just repeating for...
Some of these systems where you have to wait for multiple IO
Yeah.
objects, you just stick a pipe in there, right? A single pipe to do it in the way.
Yeah, so the someone in the audience says that it's possibly there to wake up the code every now and then to see that something happened. My suspicion as well, but I couldn't find any code or comments or Git commits that supported that idea, but yeah, makes sense. So I think this is the most important and the shortest way to explain how a scheduler, how the scheduler works. So it differs from thread, where you as a programmer are responsible. I'll put in back my slides. You as a programmer are responsible for the concurrency of your program. The advantage of that is that you don't have any useless waits, which you might have with threads, because a thread gets always its turn every 10 milliseconds, even if it's blocking. And it allows you to, in a parallel concurrency environment, to utilize the CPU better. So I think we'll be seeing more now that the fiber scheduler is there, the scheduler interface there, that it will be made more use of. Event, I think, I'm not sure how you pronounce it, but they also are working on a scheduler interface implementation. And this is just some references that I started reading and was part of all the tabs that I had open. That was it, all I have.
Thank you. Maybe just take a glass of water.
Yeah.
Yeah. So it's always nice that we see that a subject is hard to grasp by the amount of questions that we get on YouTube. So there are not that many, because it's like, whoa, what? How does this even work? I see, by the way, that you linked the blog post of Van der Hillen.
Yeah, yeah.
The fourth one, he's a regular at Amsterdam.rb meetup. He couldn't make it this evening, too bad. In that, he's in the chat. Oh, he's hurraying over there. Hello, Wander. So he had some questions about how to indeed work with blocking I/O. So, given the fact that you've been diving quite deep, you have any ideas how we can move forward when doing things that are actually blocking insanely, and still you want to use thread and write your own scheduler?
Well, I wouldn't advise writing your own scheduler. I would really use something like async from Socket3. Yeah, the use case for using fibers is when you have a lot of blocking I/O.
Yeah.
And want to have more control over who gets its turn.
Yeah.
Yeah, I would really rely on production ready SchedulerInterface implementation over writing your own. I think it's good to write your own to get to know the detail, but I don't use this in production, so this is my knowledge. I think they have more knowledge over there because they are using it actually in production, like Socketry, right? Yes.
Non-blocking API requests.
Non-blocking API requests.
Non-blocking API requests.
Okay.
Yeah.
We use these concepts. Ruby haven't free versions. Sorry, version.
Rectors? You mean rectors?
Samuel Williams is the developer async VM.
Yeah.
He made this concept before Ruby released free versions.
Okay.
And we use it in production.
So you're using Ruby 3 in production and not yet. Async in production. Okay, good. Yeah. So does that mean that you're waiting to switch to Ruby 3 for some reason, or would you?
We think about this.
Okay. Any questions? Yes. Jan.
Yeah, so you started your talk with saying, I want to move away from the day job.
Yeah.
And because of that, I'm looking for various ways how to handle jobs.
Mhm.
And you didn't did that today. If you then now come back to that original question, how did this help you to answer that question, and what was your decision? Yeah, it was more that it was a trigger for me to start looking into these kind of topics again. Because when I used to program Java, it was all about threads. When I moved to Ruby, it was all about processes. Ruby is still can only execute one thread at a time. It can't do parallelism because of the GIL, which is no longer used named GIL, but
GVL.
GVL.
Yes.
That still blocks. They're working on it, but it still blocks from true parallelism. There are now Ruby 3 rectors, which actually scope the GVL to a rector, which does open the door for true parallelism in Ruby. Coming back to your question, so we are moving away. We just finished today. Thanks, Bob. We moved our last delayed job to, in this case, SQS with. Sorry? Sure, you can. Yes, thank you. But we were running into memory issues because, and that was indeed the thing that if you start multiple threads in Ruby, then your memory basically explodes. That's an all other topic. I think the guy from Hong Lee from Passenger wrote extensively about that. You need to set a magic variable or use gmalloc to counter that. But that would be the next step, to use multiple threads to process requests, because all we do is wait for I/O. You read something, you process something, and you write to the database in the background. So it's better to use threads and maybe even fibers if that's a good. If the big framework starts supporting that, I think Rails added support for it as well. Then that definitely is the way to go. Oh,
yeah. Could you use it for, like, say, stream passing XML? Like I'm saying, if you have like a very big product catalog in XML that you can't read into memory in one go, that you could have one fiber, like reading parts of it, you're getting the XML in chunks, and then pass that over to another fiber to process or pass the products that you create.
Question is whether we can use fibers to stream process XML. Yeah.
But basically, if it's blocking. If it's non-blocking, you can just use one thing, right? Because it can't do parallelism with fibers. It's just one at a time. So if it's not blocking, you don't have to use threads, fibers. Because and I think if you stream XML, you constantly get data, right? So it's not blocking. So you can still put it on if you have multiple cores. And that's the big thing about Ruby. Then still, it's either the reading or the writing thread that will run. So that won't work unless you have multiple processes in Ruby.
Okay. Yeah, I'm sorry, but I'm new to Ruby. You said no true parallelism, even though you spawn multiple threads.
Yeah.
The OS should then divide them over a course, right?
No, that's the in Ruby. That's the. Oh, sorry. You want
Yeah,
to
so the
repeat
question is about
Sorry.
from someone new to Ruby, not new to programming, as far as I know, right? No. So if Ruby has no true parallelism, why are we talking about this thing? Just my words, not yours.
Yeah, good question. Because I think Ruby will definitely go there. They already. I'm not sure how production-ready Rectors is, to be honest. But I think it was introduced in 3.0. Looking for some.
Yeah, 3.1.
3.1. Okay, yeah. So 3.1. But as far as you as a programmer, for you, it is sort of parallelism, but it's not really because the Ruby global log prevents it still.
You don't get the benefits, but you do get the pain.
Yeah.
You don't get the benefits, but you do get the pain. Well,
Now, in the context of your very first slide where you showed spawning multiple threads.
Yeah.
Those are not parallel.
No, not in Ruby.
so the
So
question,
you always need to have multiple processes if you want to leverage all your CPUs.
Or use your
or use JRuby. That is
Yeah,
nice
true.
answer.
Yeah,
Yeah.
true. And Truffle Ruby as well. Also supports multiple threads. You're right. Thank you.
Not that I want to kill the fun, but I'm killing the fun here. We have a 5-minute break. Usually with talks like these, the questions pop up an hour later too. Make sure to find Lars on Slack and ask your questions there, or just go to the Amsterdam channel and ping him there so we can all learn from your question. That would be tremendous. Anyway, so it is 8 p.m. now. That means that, well, 1 minute past. At 6 minutes past 8, we're going to continue. So take a break. See you soon.
Thank you.
Oh, Oh, hello. Oh, hello. So that means that you're back from the break. Well, almost. Oh, yeah. Yep. It was good pizza. Anyway, you're not here to hear me talk about pizzas or actually see me eat crisps while being live. Nope, we're not going to have any of that. I'm going to introduce the second speaker to you. Everyone in this room can already see it because I'm putting this thing on a big screen here, so you already know. But Jonathan is an architect at Doctolib. That is the website for booking medical appointments in lots and lots and lots and lots of European countries. He's been working on C++, Ruby, JavaScript, and except for some programming language, expressive code, design, legacy code, and well, he's been working on testing for some 10 years. That's, by the way, also the subject of this talk. It will be about testing until it's detestable. No, it's called differently. Do we have a mini screen? Yeah. It would be nice if I could hear you, but I can't. What is going on here?
Can you hear me?
Yes! Sorry, it was me. I was doing something wrong. But hey, I've been causing so much technical difficulties today. I can have this one as well. Oh, yeah. This is not about things that are detestable at all. Anyway, Jonathan, I would just like to say enjoy and, well, take it away.
Well, thank you. Hello. Hello, Amsterdam. I've always wanted to start a talk like that. It would have it even better in person when we would feel the excitement going over the room, because we're going to talk about testing. How exciting is that? I don't know, but I find that quite exciting. So about testing, I don't know about you, but I've been struggling most of my career about testing. It's never been easy. How to write tests? How to write tests on existing code? Should I write unit tests? Is it difficult to write? Should I write end-to-end tests? What should I do? Never easy. For the most of my career, I've been following the guideline of the pyramid, the testing pyramid. So the testing pyramid is about having lots and lots of unit tests. Like if we could have tests for every class, every method in the code base, that would be the best, and have very, very few end-to-end tests. So that's the general idea of the testing pyramid. Now, that was the principle I was trying to follow for years and years. And last year, I joined Doctolib, which is a very large website to book appointments in France, in Germany, and in Italy. And I was surprised to see that there, the testing strategy is not really about the pyramid. Actually, it gives a large place to end-to-end tests. That's about 1/3 of the whole body of tests that are end-to-end tests. And there are other kind of tests, various kind of unit tests or sort of integration tests, but it's really not about the pyramid. We never talk about the pyramid. We don't aim for the pyramid. We don't have any code coverage to make sure we've got lots of unit tests. So it's completely different from what you could expect if you're familiar with the pyramid. Now, on the other hand, that website is working quite well. There are tons of users. They're generally quite happy. And we ship 3 times a day the whole website. And Doctolib has had awards. It's the number 11 favorite company for French people. And it's the company that has the most impact on the daily life of French people in 2021. Now, booking medical appointment in 2021 was pretty fashionable to get vaccinated, but still, if you don't have a vaccination campaign and you don't have, does it mean that you have to have a pyramid? No, it doesn't really make sense. So the purpose of this talk is to think about how to build a testing strategy, what kind of tests to use in code, if we're not following the pyramid. We're going to start and understand the reason behind the pyramid and question that, and we'll see some principles that are more generic than the pyramid, and that I just find them easier to follow, and that make more sense. So before we begin, where does the testing pyramid come from? The oldest reference I could find about the testing pyramid is this book, Succeeding with Agile, which was published in 2009. And in this book, page 312, we see that very famous shape of the testing pyramid. And the text that goes with it is that, and essentially, text says that end-to-end tests have problems. End-to-end tests have problems. In particular, they are brittle, which means that if you add something on a page that has an end-to-end test, you can break the test, even though you're adding a feature that's completely unrelated to what the test is testing. So they keep breaking for no good reason. And they're difficult to write, and they're slow. You can't run them every day, and even not several times a day. Now, this text was written in 2009. So we see that it doesn't talk about unit tests. It says end-to-end tests have problems. Now, we have to test the code somehow. So if we don't test that intensively with end-to-end tests, then we have to do something, then unit test, right? And lots of it to have good coverage. Now, we are going to reflect on all that, question if this is true, if this is still true today, and if this is the ultimate vision of tests. And I don't think it is. In more detail, we're going to start by checking if indeed, if we had lots and lots and lots of unit tests, is it better? And then the book says that the end-to-end tests are brittle and slow. Is that true? And is that still true today in 2022? And then if we follow something else than the pyramid, if we don't follow the pyramid, then how do we improve our test if it's not just about increasing coverage? And then we conclude with another set of principles, which I follow today, and that made testing so much easier to understand for me. Is that okay? Are you still with me here? Yeah. So, is that true that the more unit tests, the better? If it is true, it means that unit tests have more benefits than cost. So what are the benefits of unit tests and what are the costs of unit tests? Well, the first benefits of unit tests that comes to mind is that they are fast. Another benefit is that they're easy to locate, meaning that if you change some code somewhere, well, the unit tests that test that code are right next to it. It's like a file not just next to it, or in a directory which is called /test, for example, but they're easy to locate. Another advantage is that since unit tests are testing, every test is testing such a small amount of code. If a test is read, then the problem is in a very small place in the code, so it should be easy to track down and find out. Now, there are other benefits of unit tests, but those are the one that come to mind immediately. Now, what are the costs of unit tests? Do they have costs? I mean, it takes time and energy to write them, but that's also true for other kind of tests. But what are the costs that are specific to unit tests? I think this is the most underestimated thing in testing in general. So what are the costs of unit tests? In one word, one of the biggest costs of unit tests is that they need to be maintained. Said another way, unit tests that are fast to run, but they can be slow to maintain if they are not designed properly. To understand what that means, let's get to an example. So this is a function that takes a first name, a last name, and that returns a formatted full name, right? Very simple Ruby function, really nothing special about it. We have that, let's imagine we have that in our code, and we write unit test for that function. So we test that it works with a first name and a last name, and we test it without a first name, without a last name, and we could even have even more edge cases. We could test it with a nil or with a number or whatever. Let's imagine that we have plenty of unit tests and we are happy with the coverage of that function. Now, with this full name, we use it in another function. This function takes a name, which is the full name, the formatted full name, and it writes an email, right? And it uses the full name to do dear Mr. such and such, or dear Mrs. such and such, or dear just such and such if there's no title which is specified. And the email does its thing, it handles languages and so on and so forth. Arguably, in production code, we could have used like some I18N library, but just for the sake of the example, let's say this is representative of a simple piece of code. Now, we also write plenty of tests for that function, testing all the combination, and we're very happy with our code. Now, when we look at it, we can actually do some refactoring, or maybe we have to add a new feature and we want to change the code a bit, and we realize that there's a bit of duplication in there. The line with the dear gender equal male and so on seems to be repeated. It's not quite the same between the two languages, but it looks like the same. And when we think about it, it may be a responsibility of the other function to format the name with the title of the person. So let's go and refactor this code. So we go back to our previous function and we add this responsibility. It makes it a bit more complicated, but arguably this is higher in terms of cohesion, because on the other hand, this one is only focused about writing an email, which is great. Now, did I break something when I made that refactoring? Well, to know that, we launched the tests. Now, if I launch the test of this function, they are all red. And if I launch the unit test of that function, they're also all red. Now, does that mean that I broke everything? I don't know. Maybe I forgot a space, or maybe I added a space between the title and the first name. I have no idea. Which means that I need to rewrite all the tests, which is additional work, and it's not the most pleasant work you can imagine. Like, you think you're finished and you discover there are tests that you need to adapt. And also, those tests, they don't provide any coverage, because I don't have a test that was green before and that remained green to make sure that I didn't break anything. But tests are supposed to give us the freedom of refactoring, but those, they don't. Actually, if we have a pyramid, it means that all the edge cases are tested only here and not at another high level, which means that this is our only coverage. So there's no coverage, so we can't do the refactoring. So those tests, they locked us into the existing code, which defeats the purpose of tests. So as long as we change things that are behind the interface that's being tested, it's all good. But if we change the interface, we just can't, right? Or if we do, it's very risky and it needs a lot of work. Now, the interface, it's obviously the parameters, the order of the parameters, the name of the function, and so on. But more importantly, it's the responsibilities of the function. And refactoring is about changing the responsibilities of functions, essentially. What we see here, if I put that differently, is that tests make you commit to interfaces. When you test an interface, you commit to that interface. This is, I think, very underestimated and quite important. So important that it's worth reading it again in a different color, in red. And let's read it in a different font. Tests make you commit to interfaces. And to really leave a strain in your brains, I'm going to show it to you in Comic Sans with a spinning animation. This is very unfair, but that's so important and underestimated that it's worth thinking about it. Tests make you commit to interfaces. Now, going back to the benefits and the cost of unit tests, this cost is a commitment, right? Because it will hold you back later. So we've got here a first testing principle. Test the interfaces that are worth committing to, that you're prepared to commit to. Now, what are the interfaces that are worth committing to? Well, sometimes, like I suggested, committing is a cost. And in particular, if you are unit testing a function that is poorly designed, that doesn't have a clear purpose, and that is unstable, and if you're working with legacy code, I'm sure you can conjure up in your imagination a function you've been working with that has a poorly designed interface, or if you test that interface, you commit to that interface, and this is a heavy cost. Now, in general, if you have tests, if you commit to interface that are right in the middle of the code of a team, it's just a commitment that you take for the future, and that it's just a cost. Now, does that mean that we should never do unit test? Absolutely not. Does that mean that we should always do unit test? Absolutely not. It's just a benefit and a cost. And when you make unit test, you have to choose your interfaces so that the cost of commitment is worth all the benefits in terms of speed and easiness of everything, all the benefits that the unit tests bring to you. Now, there are cases where committing is not really a cost. For example, if you have interfaces that you design for stability, right, that you put care into their design, and you've designed them for the long term, then committing to them is less of a problem. It's less of a cost because they're not supposed to change. One example that comes to mind is algorithms. It's a very, very simple example because the specification for an algorithm, for example, a sorting algorithm, it's objective and it's going to stay the same forever. Now, it's not the only example. You can also design business interfaces. You can design them for stability. And there are cases where committing is actually a benefit in itself. For example, when you're writing code that's being used by another team, if you commit to that interface, it means that the other team can rely on your code, and they know that it's not going to change every day. And all the more so if that code is used by several other teams, and even more if it's a public API that's used by the outside of your company. Now, so far, we've been talking about code interface, like interfaces in code, like classes, methods, functions, and so on. Now, there are other kinds of interfaces in the system. Let's take an example in a website. So a very simplified view of a website is that there's a user that uses a device like a laptop or a mobile phone, and the device has a browser. The browser has the front-end code. The front-end code has, for example, at Doctolib we use React, so we have React components and other kind of JS stuff. And the front end calls the back end. The back end is itself an interface, like an HTTP interface, and we happen to use Ruby on Rails, which is a model view controller pattern. So we've got controllers, views, models, policies, and various kind of things. and there's a database. Now, in this drawing, every rectangle, it's a kind of interface. And just like unit tests can test methods and functions, there are technologies to test all those kinds of interfaces. Now, just like with the interfaces of functions and methods, testing those interfaces make you commit to those interfaces. Let's see an example to illustrate. The case of testing front-end components. To test React components, there's this very nice library, which is called React Testing Library, that allows to render one particular component and check that the DOM is what we expect it to be. And let's imagine we do that. Within the test, there's no internet. So when there are calls to the backend or when we expect a response from the backend, we need to do something about it. So what do? We do a fake. It can look like that. For example, this is a fake with MSW, which is a nice library as well. And in this fake, we agree that when the React component called /greeting, the fake returns a payload containing hello there. Now we can test all our edge cases. It goes very fast. We're very happy about it, and we've got our front end covered. Now we also have to test the back end. So we may test that call the backend in Rails. That's controller tests. Cool. Now we've got everything covered. There's a problem. The problem is that if the front end and the back end get out of sync, then no test will notice it because everything works in isolation, where we don't know if the contract between the front end and the back end is respected. So the system can break without any test noticing. So that's a problem. So we can also add a kind of test, which is contract tests, which essentially make sure that the fakes of your front end match what the back end returns. And now we are covered every step of the way, and every step is tested locally, and it goes blazing fast, and we're very happy about it. Now, if we do that, we've taken commitments. We've taken commitments to the contract between the front end and the back end. And also, we've taken a commitment to the interface of the component, because a React component takes inputs as props and has outputs, which is what it renders, and it has responsibilities. So if we change that, we break the commitment to the interface of the component. So just like before with unit tests, if the contract changes, tests need rework and they give no coverage. And changing the contract between the front end and the back end is something that we do all the time. It's just regular refactoring when we decide that that thing doesn't make sense, that it's done in the front end, it should be moved to the back end. Okay, let's do that and move on. If we don't have any commitment on those contracts, you can go very fast in your development. So unit tests can be fast to run but slow to maintain, whereas high-level tests like end-to-end tests, they let everything in the system free to change. You can change the contract between the front end and the back end. You can change any class, any method, anything, and you still have your end-to-end test that you don't have to update if it's written correctly, and we'll see that a bit later. And you've got tests that are green before and green after that give you coverage. So end-to-end tests are slower to run but faster to maintain. Now, does it mean that we should do 100% unit test? 100% end-to-end test? Absolutely not. Should we do 100% unit test? No. Both of them have advantages and drawback, and it's important. It's important. Sorry. Go. It's important to understand the trade-offs. Sorry, just hold on a second. Sorry, let's get back to what we were saying. That's just a break. Now, so yeah, they both have advantages, drawbacks, and it's important to see that. And it's not just about having lots of unit tests and a few end-to-end tests like the pyramid is suggesting. Now, end-to-end tests, they also have the advantage of testing the user experience, obviously. And there are the tests with the least amount of mocks. And mocks are very unpleasant things because they also make you commit to an interface because the interface is written in the mock. Right. Now, we started all that by saying that end-to-end tests have problems. They're brittle and slow. Now, are they brittle? 20 years ago, when that book was written in the 2000s, end-to-end tests were very different from that one they are today. It was about having humans clicking around, recording their actions and recording the displayed result and comparing that displayed result with what you get after changing the code. Today, it's different. For example, there's those libraries, Selenium, which is something that allows you to drive the behavior of a browser, and Capybara, that is a Ruby wrapper over Selenium. Now, I'm not saying those are the best of the market. It's just those that I happen to use, but they just illustrate what we can do with end-to-end tests. For example, on our website, we've got, for example, this button, which I accept, which means I accept in French. And if you want to have a test that clicks on that button, you can just call that function click on and pass it j'accepte. This function click on is very powerful because if you change anything on the page, anything else on the page, the test doesn't break. If you change the style of the button, the test doesn't break. If you change the position of the button, the test doesn't break. Now, you can want to test the style and position, and that's a completely different kind of test, like regression, visual regression testing. But those cases don't break your tests. Now, also, end-to-end test the user experience. There's no better way than clicking on a button. I mean, to call click and to simulate the click on a button. But also, the Capybara is like a robot, right? It's a piece of software. So if Capybara can click on your button, it means that any piece of software can click on your button. And that's quite important because your website is going to be used by pieces of software. For example, it's going to be used by screen readers and by search engines crawlers. So if Capybara can click on your button, then it gives you some coverage, not everything obviously, but some coverage on accessibility and SEO. Because if it's not a button, if it's just a text, clicking doesn't work. Now, to make end-to-end tests less brittle, we can do the same things that we do to make regular code less brittle. For example, we can encapsulate the details, the implementation details. So what are the implementation details when it comes to end-to-end tests? One example is HTML and CSS. Let's take an example. This is a page on our website where doctors can see the history of their requests to the support. Now, we want to test that, for example, on the line where there is first subject, we want to test that there is written phone and ongoing. One way to write it is that using the find function coming from Capybara, and it says that you should find an HTML element which is of kind tr with a text which is first subject. A better way to go about it is to wrap that into a function that we call row of, and it makes the test more expressive, and you don't care that it's a tr. What you care about is that it's a row with that subject. And you would do that in regular code to make it more expressive and more robust, and we can do the same with test. Another example is page objects. So let's see an example. This is a web page on our site where you can book an appointment in a hospital. And On the right-hand side of the page, there's this question you have to answer. Have you already been to that particular hospital? And you can click yes or no, and the rest of the funnel depends on where you clicked here. So the test can want to click yes or no. Now, if you just do click on yes, first, if there's another yes on the web page, that breaks. And also, if you read your test and you see just click on yes, it doesn't really say what it does. It's difficult to maintain. Now, you can wrap all that bit of CSS to locate that particular part of the page and wrap that into a nice interface that you can call from the body of the test to say, for example, select patient is new, which clicks on no, or select patient is not new, which has the effect of clicking on yes. And from the test, you just read that and you hide all the implementation details, the low-level CSS and HTML. So are end-to-end tests brittle? Or if you have good tooling and if you invest in the code quality of your test, it goes a long way to make your end-to-end test more robust. So this is a second principle that we have, is to have good test tooling and invest in the quality of the code of our tests. Now, the other problem for end-to-end tests was that they are slow. So are they slow? If you compare one unit test with one end-to-end test, the unit test is so much faster. A unit test, it depends. It can take some like tens of milliseconds to run. And an end-to-end test that opens up a browser and clicks around, it can take seconds or a dozen of seconds. Or, I mean, for long tests, it can take a while. I tested lots of things like long flows. Now, 20 years ago, that was the end of the story. Today, it's different. Today, it's reasonable to have clusters of servers that runs your test for your CI, right? And then they can run them in parallel. What matters ultimately is the feedback loop, the time to have feedback about did you break something or not, right? It doesn't really matter how much time was spent in total on all the servers to get that information. Now, having multiple servers, it has a cost. So there's a new parameter. Your system can be cheap or expensive. And there are 1,000 ways to design your testing system, your CI system. Some are simple and some are complex. About the cost of tests, end-to-end tests that have a browser, they can be flaky because the browser sometimes can slow down a bit and it makes the test flaky. Now you have to relaunch the test or work on the flaky, so that parts of the cost. Now back to simple and complex, your system can be more or less simple and complex. And you can't have everything. Actually, you can have everything by not launching any tests. It's fast, simple, and cheap, but that doesn't really, it's not really what we want, is it? Now, you have to pick a trade-off. One possible trade-off is something that's simple and cheap, but slow, is to launch all the tests on one machine. Maybe it makes sense for like a personal website where you make a commit every week, for example, but on a professional website, it doesn't really hold. Another trade-off is something that's fast and simple, but expensive. It's to launch all the tests for all the commits. So that's very simple, but on many machines. And that's expensive because you have to rent many machines. Another trade-off is something that's fast and cheap, but complex, is to launch not all the tests, but a subset of the tests that you select relevant tests on few machines. What makes it more complex is to make sure you select the right tests. So you can't have everything, you have to make a choice. At Doctolib, Doctolib has been around for like 9 years. And so far, since the beginning, it was on that left side. We launched all the tests for all our commits on many machines. Now, the company is growing quite fast. So this is becoming expensive. So we want to move a bit. We don't want to trade all our simplicity for price, but we want to adjust a bit, and we are starting to select subsets of relevant tests. We're not the only ones to move in that direction. For example, Shopify, they clearly position themselves also in this area of trade-offs. And we've just making that move now after 9 years of being around, having millions of users, and we have 40,000 tests, and a third of them is end-to-end tests, like 15,000 tests are end-to-end tests. So it's only now that we start to adjust. So there is room for smaller companies to have this strategy. Now, are they slow? It's just one parameter. The thing is, it's a trade-off. And this concept of trade-off, we also saw it earlier when comparing unit tests and end-to-end tests. So we see that this very concept of trade-offs is central, is in testing, it's essential. This is our third principle. We can't really teach engineers how to write tests, but we can teach them the trade-offs of tests, and then when they master those trade-offs, they can make the right decision for every situation. Now, if we are not targeting a pyramid, what should we do? How can we improve our tests? Well, if we go back to why we write tests, we write tests because we don't want things to get broken, right? Now, what exactly don't we want to get broken? Obviously, there are what we show to the user, including the software that uses our website. But also, so that's an argument in favor of end-to-end tests, but not only, that can be an argument in favor of unit tests that are representative of usage. Now, there are other usages. For example, anyone can send HTTP requests to the backend. So we want to make sure that we only return what we should return, that it's only the data that the person is allowed to see, and so on. We don't want that to be broken. We also have use cases for developers, like logs about what's going on in the system, and for the data, like how is the application used, metrics. We don't want any of this to be broken. Now, how does that work? How can we have an impact? Well, it's about being sensitive to the usage of the product. How does that work? The usage of the product. Let's take the example of the use cases of the users. At first, they are in the minds of the users, right? And then the user research team that tries and understand that. And then the PM or PO understand that information and make specifications. They pass them along to developers, and developers, they write the tests. They write the end-to-end tests. It's a funnel, and at every step of the way, there is information that gets lost. Now, our impact as developers, it's to lose as little information as we can when it's our turn. Said another way, we want developers that are sensitive and interested by the usage of the product. Now, how do we do that? It's a completely different topic. I don't want to get into it. Maybe we can talk about it if you're interested in the Q&A. But the takeaway is that we want tests that reflect the usage of the product. Now, it doesn't mean that all tests should be like that. Like, for example, testing a sorting algorithm, it's a bit far from the usage of the product, the actual sorting. So, and this makes sense to unit test the sorting algorithm. So it doesn't mean that all tests should reflect the usage of the product. But if you want to improve your test, one way is to understand the usage of the product and have that written in your tests. In conclusion, before I joined Doctolib, my testing principles was just to follow the pyramid, have as many unit tests as I could and as few end-to-end tests as I could. Now it's completely different. The testing principle that I follow is testing the interfaces that are worth committing to, have good test tooling and high test code quality, mastering the trade-offs of testing, and reflecting the usage of the product in the tests. Now, that can lead to a pyramid. If all your interfaces are perfect inside of your software and you have very limited resources to have end-to-end tests. Now, currently at Doctolib, we have a square, really, because it's like 1/3 of end-to-end, 1/3 and 1/3. But we didn't aim for a square. Whether respecting those principles lead you to a pyramid, a square, a butterfly, a star, any shape, it doesn't matter. What matters is to understand why you are testing. Thank you.
So you didn't hear all the applause because I was that bit late to the cam again. But well, we had some good time. I have seen a lot of peeps looking at it like, So, well, that's the fun of me being here, that I can say that a lot of people were looking really interested in the topic. I have some questions. Do you have some questions, or shall I just kick this thing off? Oh, Jan Pas.
Question that I have is, if you look at testing frameworks such as Jest in JavaScript, one of the things that I've seen them doing is introducing little hooks to components. So you no longer use an API where you say click on I accept, but you use an API where you say click on the attribute with the I accept string. And the idea behind this is that that it supports multiple languages, and that you are also free to change the text on the actual button. And I wonder how you feel about it when you're saying about I want to commit to an interface, because the text on the button is also a sort of interface in that sense.
Did you understand the question? Do you want me to repeat it?
Yes, please. Yes, please.
So it will be less prose. Sorry, Jan. So Jest has some hooks which allow you to say, well, click on this string, and then you are already more committing to the interface.
Yeah. So you're not committing to the actual text on the button.
You're not committing to the text on the button, but to some identifier of the button.
Yeah, indeed.
How do you feel about such an approach, getting it closer to testing an interface instead of, well, working with non-connected parts, so to say?
So if I understand the question correctly, I mean, with Jest, you can simulate the click on the button. Is that the topic? Yeah. And with Jest, you can only
what you can do, you can click on an element with some identifier. So you can give that identifier a good name, which you refer to in your code, and then your front end can click on that element based on that identifier, and your backend will just spit out that element with that identifier, and therefore they're already connected.
Right. So first, about the identifier, if you write the identifier in your test, you commit to that identifier, and you have to be sure it's the right one if you don't want to change your test. Another way to go about it is to have a page object which has a method that returns the identifier, and the method is expressed in business terms. So that you can change your identifier, or you can change how you get to that element. Now, if I'm not mistaken, with Jest, you're only testing JavaScript code, right? You don't have the backend, do you?
Maybe I could, sorry, I meant Cypress. Sorry about it. I meant Cypress.
He meant Cypress.
Right. Okay, I'm with you. Yeah. Well, Cypress and Selenium, they're different tool, but they both drive a browser. So yeah, you can do some click on an element, and I think that's great to have the wording encapsulated in your page object. Yeah.
I have a question. So, do you have this presentation? Are you doing this on a monthly basis when onboarding new colleagues, or how do you onboard people to this testing architecture?
Yeah, we have it every month. We recruit dozens. I give it to them every month.
Now, knowing that, lots and lots of people are making appointments to, get shots for, whatever. I mean, just remember the last 2 years. Are you also testing in production to ensure that the whole thing is up and that, you can be confident that not only the test suite passes, but also everything in production is hunky-dory?
Well, we have monitoring production quite detailed about everything that's going on really on the servers, about the errors, the amount of errors that go back to the front end, or any kind of like performance monitoring, the load on the DB. We've got very detailed monitoring that's more SRE on the SRE side. Now, about the applicative test, we only have our test suite and we roll out, and if there's a big problem, then we can still roll back without any impacts on the user. But in practice, we just run the tests and roll out.
Okay, that clearly proves enough visibility. I have a question.
Yeah, so one of the advantages you mentioned for unit tests is debuggability. It's because the scope is so small, it's quite easy to debug a problem. What about these end-to-end tests? What tips do you have to improve the debuggability of failing end-to-end tests?
So the question was, the unit tests have a small scope. What tips do you have to improve writing end-to-end tests to help scope it down a bit?
Debug the problem if they fail.
Debug the problem when they fail.
Right, that's a great question. Thank you. Well, to debug an end-to-end test, there are, I think, two ways to go about that. First, if you launch your test, all your end-to-end tests, all the relevant tests at each commit, then you know which commit broke the test. So that's a very strong lead. And often you just look at the code and you realize, oh yeah, okay, that's why I understand. I just didn't think about that edge case. And then you go and refactor all the code and the test is green. Now, in fewer cases, it's not obvious how you broke the behavior. And then it becomes like a bug, like analyzing a bug. And so the question comes down to, how can I find the source of a bug in a fast way? And this is a technique that we have to master as developers in general, independently from tests, because when you have a bug, you need to quickly find your way to the root cause. Now, how do you do that? It's about right. So how do you find the root cause of a bug? First, you try and reproduce the bug. So if the CI said that your test is red, the first thing you have to do is make sure it's red on your machine. And if it's not, there's no purpose in going forward. You have to find a way to make it red on your machine. And if you're using Docker, for example, most of the time you can reproduce on your machine easily. Now, once it's red on your machine, play around with the test case. If you change things a bit, do you still reproduce the problem so that you can sort of like bisect your way to the root cause in terms of the product? Like, this is broken only in this very specific case. Right? You can try cases that are near the case that's broken and see if it's also broken, or if it's not, until you know from a product perspective where it's broken. Then you track down the thing from a product way, and then you go to the code, right? And the idea is to go to the code as late as possible until you really reduce the scope of where the bug can be, and then you go to the code, and hopefully it's close to your commit, change it in your commit, and then you make a hypothesis about why it's broken, and then you look at the code to make sure to check your hypothesis to see if it's true or false. And if it's true, then it's over. And if it's false, then you make another hypothesis, and so on until you track down the source of a bug. Now, this technique works for bugs in general or for difficult use cases in tests. And one way to find the code that corresponds to the place that you selected in the product, it's to be able to travel from the product to the code. And that's something that's essential to be able to do on your code base. And on website, the easiest way is to just look at the wording on the page and try and find where that wording appears in the code. Now, on other application, like on not a website, but on software that you install on your machine, then you have like a UI framework that's embedded in your software. Well, you need to be able to find your way from what's displayed on the screen or on the REST service, on the logs or whatever your interface is. You need to find a way from there to the code, and you have to learn how to do that just one time, explore the UI framework to find your way, and then you can move back and forth from the code into the product. But that's quite independent from testing.
I see some, yeah. I see some nodding here. There is a question from YouTube, but before we get there, I just want to make a very annoying selfie here. Give me a second. So anyway, the question is, how do you even pronounce that right? Do you have a QA testers in your team, or are all the devs the testers?
Well, as it happens, we don't have QA. We roll out 3 times a day. We don't have the time to make humans test everything. Now, I'm not saying QA are a bad idea in general. Maybe QA that don't block the rollout could make sense. Like they could have their own cycle, and they can make exploratory testing, and they could write their own end-to-end test and have a mindset of looking for bugs, and that could make sense. Now it happens that we don't have that at the moment.
Okay, then a somewhat related question: how do you keep the non-text peeps in the company aware of, well, how the tests, how they pass, things that go right, things that go wrong? Is there visibility outside the development team, or is that something owned and only visible for the engineers?
Well, there are the engineers, and there's the team that maintains the CI. There are a bunch of developers that actually work on maintaining and evolving our CI system, and they are also involved along with the developers in the test results.
We have end-to-end capability tests in our environment too, but we also find that front-end developers can break those tests, but maybe aren't necessarily equipped to fix those tests. I'm curious if that's a challenge that his team has experienced and what they do to address it.
Okay. So the question is, we have some front-end devs in the team that they can break the tests, but may or may not be completely fitted to fix them again. Do you have some tips on how to improve that?
So front-end developers that would break.
Like the front-end devs,
Is that the question? What kind of test are you?
So if you have front-end developers that are writing a framework,
I'm just going to try to liaise here. So you have some front-enders trying to change code and breaking tests in
the end-to-end capability test
yeah.
in Ruby.
So they break the end-to-end test that's just sit in Ruby in Capybara, and so the front-enders, they change the website and everything, or some things break, but they are not equipped to fix it because it's in Ruby. How do you solve that?
So in our company, we happen to be full stack developers, all of us. So we write the front end and the back end and the tests, so we don't have that problem. Now, Do you mean that you have developers that write code and they can't write the test, or they can't maintain the test for the code they write because there are end-to-end tests that encompass the code that they write? Isn't that a problem?
Well, so the front end are making changes to the front end, and as a result, Capybara goes on red because this is testing something that happens in the front end. So the Capybara tests something like how the page looks like, how the page behaves, and the front ender who made a change isn't able to fix it because they may or may not know their way around in Ruby and Capybara.
Yeah, I understand that. Sounds like a problem because there's it sounds like there's a split in the ownership of the whole feature, because the feature is the code and the test that test the feature, even though they were written after or before. So it means that the ownership of the feature is split across teams, and I understand how that can be a problem. And I mean, it's not specific to testing. If you have ownership of one thing that's split across teams, it's sure that there aren't going to be conflicts or any kind of problems. I mean, I don't have any specific solutions to that for testing. I found it made more sense to have the ownership of a feature only in one team.
Well, I think that is a perfect valid answer. Thank you. Another question from the audience?
Yeah, we have a product which has maybe 8 or 9 different components in the chain. So you'll have, say, the front-end registration, you'll have a mobile phone validation piece, you'll have a something which does the payment, another piece which checks for products and looks for products, and then another piece which does a connection to an API to do purchasing. So each of these teams can do 5 to 10 deployments a day. How would you have a strategy in this case? If we were going to run an end-to-end test every time a deployment was done to production, we'd be doing 50 to 100 end-to-end tests a day. Is there a way you could, do you have a strategy for doing a subset of those tests in certain circumstances instead of doing the whole test suite every time?
I think I heard most of the question. I'll reformulate and just let me know if it's not that. So you've got several teams working in microservices, if I understand correctly. And there are like 4 or 5 major parts in your front end. One of them is connected to the back end. And you release asynchronously from one another. And you have hundreds of end-to-end tests. Is that what you said? Yeah, hundreds of end-to-end tests.
Yes.
And hundreds of one. Okay. So right. Hundreds of end-to-end tests. It doesn't look like a lot for a cluster of machines. Like for one machine, it's a lot. For a cluster of machines, it sounds like in the ballpark of what a cluster of machines could eat in a reasonable amount of time. Now, I don't know your test or your system. I may be wrong on that, but maybe it's worth investigating the just power of running those tests. Now, that said, if you have very independent pieces in your system, but with interactions, because I'd imagine that all the major part of your front end communicate with one another and are owned by different teams, most importantly, it means that some of them have interfaces that are used by other teams, if I understand correctly. And it makes perfect sense to write tests against those interfaces because you want to make a commitment to the other teams, right? So it makes sense to write those tests and those interfaces. Now, I think the most important question there is how you design those interfaces. And you want to design them for stability. Now, how do you design an interface for stability? First, you want to have one very clear and unique and specific purpose for your interface, right? Or for your component. So that it's only it won't change if something in related changes. Now, another thing is that you want to be intentional in your dependencies, because since the various parts of your system communicate with one another, it means that one uses the other. Let's say that, for example, A uses B. If B changes, it means that A has to change, and all the tests of B have to change as well. Now, if you don't want that to happen, you can manage your dependencies, for example, with dependency injection, what they call hexagonal architecture, which has nothing to do with the hexagon, with what they call clean architecture. It's a whole topic, but it allows you to be intentional about who depends on what, so that you've got parts of your system that impose on the other part of your system, that impose the interfaces, right? Like even if A uses B, A can impose the interface that B should implement with like dependency inversion. If you look up dependency inversion, you can do that. And that allows you to choose who is stable, who's not stable, and then you can write tests around the stable interfaces. Hope that makes sense.
I see thumbs going up, so that makes sense indeed. Personal question: are you part of the Netherlands Ruby Slack, Jonathan?
No, I'm not.
Are you part of this Slack?
No, I'm not.
You're not. So how can we ask you questions then?
Oh, yeah, I can.
Yeah.
I'm not often on Slack. I can give you my email. I don't know if you see the slides. You have my Twitter handle, so you can ping me on Twitter, or I can just give you my email. It's Jonathan.Boccara@Doctolib.com. So feel free to just send me an email or ping me on Twitter. I'm always happy to talk about testing and design.
Okay, good, nice. And with that, I would like to wrap up this presentation. And by the way, also the Ruby Amsterdam meetup of today. I wish you all a good evening and see you in a month, because we're doing this monthly now, right?
Yeah.